Hi, it's CNT140, Chapter 2 of our fiber optic book. We're on the section now on splicing and termination. So again, they're giving us a lot of terms, so reference these as you need later on. So they talk about splice, mechanical splice, fusion splice, and fusion splicer. A splice is a permanent connection between two fibers, and it might be that you're joining to make a longer fiber to connect places, or it might even be that you're repairing a fiber that has been broken. There's mechanical and fusion splices. Mechanical is just that. It's a mechanical apparatus that goes around it to keep them joined. Fusion, I'm heating up both glass stubs and touching them together so they literally fuse together. So your mechanical splice, I'm using some piece of equipment like so. The fibers go into the splice tube here in the middle, and then the clamp goes around to hold them in place. And there's your mechanical splice there. Meanwhile, the fusion splice, you're actually preparing both stubs, getting them super close together. An electrode actually arcs across there to heat them up, and then the machine itself touches those two stubs together, lets them cool, and now they're welded together as if they're one piece of glass. So I strip the fibers, clean them, cleave them, put them in the splicer. The splicer, here's the two stubs. Here's the glass stub here, glass stub here. There's the arc that arcs across, heats them up, and then machine just gently rolls those two fibers towards each other to touch and lets them cool. And then when you're done, you put a splice sleeve over top to give it protection so that splice does not break. And that's all done with a fusion splicer. And that actually is as I look here, it's actually showing the alignment on the x-axis and the y-axis, kind of like front and back, up and down. It's aligning those two fibers and aligning the cores, doing some core alignment here to get them to line up, almost like taking two garden hoses and lining them up perfectly so water moves from one to the other. When I'm dealing with terminations and splices, there is some hardware that I'm probably going to end up using. Here's a patch panel for connecting one length to another, and that's actually here to support the fibers. If I have a bunch of splices or breakouts, I might need to actually have trays that are going to support that splice or that fiber so it doesn't break, and then slide into the box, if you will. So there's some special hardware to protect and store any of these fiber connections. Now as we get into the performance of the fiber, we run into lots of terms. The first one, attenuation, that's the weakening of the signal over distance. Now we're going to reference or represent that with decibels. Decibels, the strength of the signal, how much it might have weakened over time, over distance, if you will. Bandwidth is how much are we able to support on this link? How much bandwidth are we able to support on this link? Decibels is a unit of measure of signal strength, in this case optical power, and it's a logarithmic exponential type of scale. So a negative 10 decibel means a reduction in power by 10 times. Negative 20 is 100 times. Negative 30 is 1,000 times. So you can almost think of it as like 1 0, 2 zeros, 3 zeros kind of deal. If that helps you, put your finger on that quickly. This optical power is referenced at an arbitrary zero level, but it's used to measure loss, how much has been lost over time. Meanwhile, decibel milliwatts, dBm, optical power reference to 1 milliwatt, and this is used to measure the optical power from transmitters or at the receivers, the actual true power, if you will. Optical loss, optical power. Here we're putting all these pieces together now. Optical loss is the amount of optical power lost as light is transmitted through the fiber when hitting splices, couplers, etc., expressed in decibels. This is a relative reading. So, you had a signal strength of 10 here. It's now 8 on the other end. I've had a loss of 2, if you will. It's relative. The optical power is measured again in decibel milliwatts, dBm, and this is an absolute measurement, reference to standards. So you measure absolute power to test the transmitters or the receivers, the strength of them. When I have signals across fiber, I'm going to run into what's called dispersion. Dispersion is the spreading out of this, the signal that you're sending across. So I send this pulse of light as a 1 over the distance. That pulse is going to spread out. And if I only have a little bit of it, my signal is still readable on the other end. But if it spreads out a lot on the other end, it might be like it will start looking at going, was that 2 1s that you sent or 1 1? You know, it's going to be harder to read. Well, there's different types of dispersion that you run into. There's modal dispersion that you run into with multi-mode fiber. Since there's multiple modes of light being sent down the fiber to represent that one, these multiple modes, and they're exaggerating here, could literally take different lengths of time to get down the fiber. One is bouncing more acutely, one's bouncing, you know, very obtusely, if you will. So here they're exaggerating by showing, hey, this mode bounced this way and got here fairly quickly. This one was bouncing up and down and got there kind of late. So it's spreading out that signal over distance. This is common, or this is a problem in multi-mode fiber. Another type of dispersion is chromatic. Chromatic is, think of the wavelengths of light. If you take light coming in the window and run it through a prism, it breaks that out into a rainbow. Well, all those colors of the rainbow are different wavelengths of light. So as I start sending a signal down the fiber, it's bending the light and almost acting like a prism and starting to break them into their component colors. So these component colors would start bending and bouncing at a different angle from each other. So the result at the end is the signal has kind of spread out into its component pieces. Okay, that again is also a problem in multi-mode as well as single mode fiber. The last one they mention is polarization. The pulse of light that's going down the fiber actually has components to it, and that's what they're trying to show you here. They're kind of like at a right angle at each other. Well, if I have stresses and bends and twists and things on my fiber, that can cause those two pieces to kind of get out of alignment from each other, and I can have they're showing you here, those pulses being kind of skewed a little bit. And that would be your polarization mode dispersion. This is a problem in higher bandwidths of fiber optic cable. There is scattering. When you send light down a fiber, obviously if there's dirt, it's going to hit the dirt and, you know, get scattered. But there's actually, in the actual glass fiber itself, there's pieces of impurity in there, but some of those are down at the atomic level, down at the ionic level, at the ionic level. Charged particles on the atoms act like little mirrors, and as light hits them, they kind of break into, almost like throwing something like a chalk against the wall or sidewalk, and it breaks out into pieces. That is scattering. Some of our wavelengths of light used in fiber are picked for a specific reason to avoid this scattering phenomenon. So when we talk wavelengths of light, here our visible light spectrum is here. The wavelengths of light used for fiber optic are near infrared, they call them, or infrared spectrum, 850, 1300, and 1550. Well, those are picked on purpose because if I look at the wavelengths of light, the amount of absorption and scattering that occurs happens at these wavelengths of light. So the absorption of the signal happens here. There's a lot of absorption at these wavelengths, so the wavelengths around them are the ones that typically get used. The tools we run into with fiber optic is you would have a jacket, slitter, or stripper to cut off the jacket, usually in like your outside plant type cables. We have a fiber stripper that's usually there to strip the buffer off of the fiber. This is the kind of style we have in our room, and there is actually different openings for different buffer sizes and so forth, so you need to pay attention to those. Here's the cleaver. We'll end up using this later this semester. This is a highly precision device to actually nick the fiber and then break that off. If you've ever worked with glass, a clean break on the edge of a glass is actually very, very smooth, if you will, if you break it off correctly. That's what this cleaver does. It actually nicks that fiber and then breaks that end off. It cleaves it off. If you do a polished type fiber connector, you might use a scribe. This is acting as your cleaver. You actually score it here and break it off, and then you polish back that stub that's sticking out. Polish it flat with the end of the connector, and that's when you run into the polishing puck. The connector fits down through there, and then you move it on top of your polishing medium, polishing film right here, and you're basically in basic terms sanding that fiber back flat. You're not really sanding, that's a little too aggressive, but it's that type of idea. You're polishing it back to be flat with the end of the connector. Some of your connectors, you're going to actually bend the strength fibers, the aramid yarn, back around the jacket and crimp them on to add strength. So you might actually be using a crimper to get those strength fibers into the connector for some strength, for additional strength on the fiber connection. I'll get it yet. Fusion splicer. This is either going to get used to splice two fibers together or splice on a connector on the end of the fiber. That's the type we'll end up doing later this semester, and our fusion splicer looks very identical to this guy. There's some testing tools we'll use again later this semester. There's an optical power meter. The optical power meter is going to measure the optical power from the end of the fiber, how much is like getting there, if you will. Well, to do that, I need a light source. That would be this part of the meter that's going to send a light signal down of known wavelength and strength, if you will. And then the meter itself would measure that signal here. Well, when you put both those together, you get an optical loss test set. You have the light source and the meter. That's what basically those two pieces are together. To do a lot of tests, you need reference cables. These would be the tester cables that go onto the meter and allow you to connect in a cable run here or a patch cable here, if you will, that kind of thing. I would end up using a mating adapter, a coupler, to connect the reference cable onto the cable I'm testing or the cable run I'm testing. There is such a thing as a fiber tracer. It's basically a light source that I can put on a fiber end and try to identify where that is, maybe on the patch panel or on the other end of the fiber, which one is showing up. Well, there it is. So this must be this end, and etc. That's helping you identify what fiber. And there's also a visual fault locator. Locator. We'll use this later semester as well. This is actually a kind of like a overpowered laser light source that if I run it through a good fiber, the light comes out the end. If I have a break in the fiber, it kind of lights that up and shows you that's where the fault is. Almost like identifying where the water leak is. When I deal with the connectors, I might end up using an inspection microscope to look at the end of the connector, to look for scratches, dirt, oil, etc. Caution, make sure there's no light source connected on the fiber, because the microscope would magnify that light into your eye and do damage. Okay, so you got to make sure it's not connected to anything. And then here's some samples of looking through that microscope. Here's one that has dirt and scratches. Here's one that just has dirt on. Here is some oily residue. Here's a smudge from a finger. Those are the kind of things you'd be looking for. Is this connector, able to be used? This connection able to be used? There is an OTDR, an optical time reflectometer, that's going to allow you to test the cable run. This a lot of times gets used on outside plant, but test the cable run for distance as well as maybe any splices or issues in the fiber. Here's some OTDRs. It takes advantage of the light reflecting back, the backscattered light, to know that. Know if there's an issue or problem. So here's your cable run. It'll see splices and so forth as little bumps, connectors as large ones, but if I have it drop off abruptly, that might be a break. And if I know my distance of the cable, and this shows up much shorter, that might be where the break is happening. So I'm getting these kind of results with my OTDR. All right, so there is a lot of jargon on fiber optic. Use this chapter as almost like a glossary or reference as the semester goes on.